Hi everyone. Let's get it started. So welcome everybody.
Hello.
Hi Claudio, welcome. So I'm here with Claudio Beatrice, that is the organizer of the Golang Torino and Golang Milan meetup. And I'm Enrico Candino, and I'm the organizer from the Golang Roma meetup actually. And so this is going to be first time with this kind of hybrid and joint meetup. So it's a new experience also for us. Bear with us, and whoever is watching the video, and also remember that there is a bit of delay, probably like 10 seconds. So just if you have any question or whatever, just post in chat. And yeah, I mean, let's get started. Do you want to say something? Do you want to add something, Claudio?
Well, no, I'm super excited. We have this hybrid setup where we have people here in Turin and in Rome as well, right? It's a pretty nice experiment. I'm super excited to have Jon. I'm a really big fan of his book. I've been, I've probably been given his the recommendation of reading it left and right over the years. So I can't wait to have him on stage. But before that, maybe you wanna say something about a little surprise that we have.
Yeah, so Johnny probably already told us also on LinkedIn on the whatever. We have a nice surprise. Basically, we are going to give away 5 ebooks of the Learning Go second edition, and
Sweet.
yeah. So if anyone wants to try to win the to be one of the lucky winners, basically there is a small survey, and you can just drop your email, and let's just add some information about you. Where are you watching the event from, and such. And I mean, it's just 2 or 3 questions, so it will be super easy. And at the end, we are going to extract the 5 winners. And so let's get started. Let's invite also Jon. I will also post the link in chat. So if you are not able to see to the form, no worries.
All right.
Hi, Jon. Welcome.
Thank you. Thanks for having me.
Hello, Jon.
Hey.
It's great to have you here. Thank you for offering to host this meetup. We have friends from all around the world. I see Brazil, India, UK. Pretty exciting.
Yeah.
So what's the topic you're going to introduce the crowd today?
So I'm going to cover today is about the first half of chapter 15 of Learning Go, which covers testing. So the basics of testing in Go, and then go through some more complicated examples, some of the built-in support. I'll talk about fuzzing, which may be a new concept to some people, and benchmarking as well in Go, so we can learn a little bit more.
That's sweet. Before we dive into the talk, I would like to ask you a couple of questions to like warm up the audience, and also because I'm curious. So maybe you'd like to take a minute or two to introduce yourself. What's your professional experience? What do you do in your life besides writing books?
I wish that was all, but no, I'm a staff engineer at Datadog. My focus actually is on making it easier for our customers to use our products. So I do some Go in my daily work. I do other languages as well. I've been working as a software engineer for over 25 years at this point. Worked in many industries. I was in banking. I've done DNS. I've done government work, educational software, lots of things.
Wow. Let's talk about the book.
Yeah.
How did you come up with the idea of writing it, and how much effort did it take to? I think it's the second edition, right?
Correct. Yeah.
In the store. Okay.
Yeah. The first edition was harder. There's a lot more. Going from 0 to 1 is harder than 1 to 2. So yeah, I've been actually doing Java development since 1996, 97. I've been a Java developer for a long time. And then when Go came along, I was getting a little disenchanted with Java, and I really liked Go. And I kind of made this transition to working a lot more in Go than in Java. And I thought, I bet there are more developers kind of like that out there who were experienced and they were using a language like Java, and they would like a book that would teach them how to write Go. Not starting from scratch, but starting from already knowing something about programming. And there's a whole story about how I actually made contact with O'Reilly. I've been trying for years, and someone who I met on the Go team at Google pointed the editor at O'Reilly out to me and said, "Talk to him. He can write a book on Go." Went to a baseball game together at GopherCon in 2019. And she said, "Instead of a book just on Java, how about just any language to Go?" I said, "That's a great idea." And so I submitted the proposal, and that's the origin of the book. It took about a year or so to write the first edition. It's about another year for the second edition, but it was a much slower paced year to get the second edition done.
And yeah, I was recently speaking with one of the folks at the Zig Foundation, and they hold the opinion that Go is the new Java, which is interesting. I don't disagree with them. But besides that, any interesting anecdote that maybe you feel like sharing, or that happened while writing the book, or maybe doing some research or anything?
Let's see. So the original title of the book was actually to be Idiomatic Go. And after I got to the first section of the book done and went out to reviewers, one of the reviewers came back and was expecting something like effective Go or effective C++ or like Java Puzzler, something that was more like very focused on like very targeted advice and not just an overview of the language. And so this was actually kind of this question, like, am I writing the wrong book? Was actually the first question that was being asked. And the second, and I was like, no, this is the right book. And the second question, okay, so we can't call it this. What name should we pick up for the book instead? And O'Reilly kind of settled on Learning Go instead as a name. And I think it actually works pretty well because it was the goal of the book. I talk about idiomatic Go a lot in the book. The phrase pops up a bunch because I want people to write code in a way that doesn't fight against the language and want to understand why they're doing things the way they're doing that. But the goal is to teach you how to use the language as opposed to just like tips and tricks.
Yeah, I personally really like the way it's written. It packs a lot of details, but it's not too verbose. So I can't recommend it enough. But okay, I'm done being like a groupie. Yeah, but it's truly one of my favorite books. So without further ado, Enrico, do you have any other questions? Or
I think that we have started. So let's say to just don't delay too much, and let's see. I don't know how long it will take. So I thought about 1 hour, maybe 40 minutes, whatever. But keep your time. So
yeah, it should take about a little bit less than an hour. But
super. Thank you. Okay. So thanks, Jon. So floor is yours.
All right. Gonna share screen. All right. Well, thanks everyone. So hopefully everyone can see what I'm have on screen. So yeah, talking about writing tests in Go, and since the early 2000s, like the widespread adoption of automated testing has really been the biggest thing to change code quality in software engineering. It's hard to believe there was a time before unit tests, but there was a time before unit tests. And Go is this language that's focused on software quality, software engineering. So it's not surprising that Go includes good support for writing tests. And I'll talk about some of the basics of this first. There's two parts. There's library support and there's tooling support. So there's the testing package in Go in the standard library, and it provides the types and the functions and the methods to write tests. And then you have the Go test tool that's bundled with Go that will run your test and generate reports for you. Now, unlike many other languages, Go puts its tests in the exact same directory as your production code. And because they're in the same package, you can test your unexported functions and variables. And I will focus a little bit on how to write tests that only test your public API as well. All the code I'm showing, by the way, is available in the GitHub repo for the book. It's a link on screen right now, but it's github.com/learninggo book 2e. Now let's start with a simple program here. So we have a very simple function we're going to write a test against. Function add numbers takes in two values, x and y, returns back an int, and it adds things together. If you see a bug, that's very good, because we're going to show that there's a bug by writing a test against it. And let's look at a couple of things here in our tests. So first of all, declare the package, same package as our function we're going to test. We are going to import the testing package from the Go standard library. We're going to write a function. And you'll see the function starts with the word test. Every function in Go, that's a test function, starts with the word test. And then you give it some name after that makes sense for what it is. We're testing an unexported function, so I traditionally do an underscore and then the name of the function. The test function has one parameter of type pointer to testing t. Traditionally, you call it a t is the name of the variable. And then you just call the function. By the way, the x and y you see on screen, that's IntelliJ doing that. If you're not using IntelliJ or Golang to write your code, use IntelliJ. I don't get money for promoting it, but it's great. And so we're going to pass in 2 and 3 to the add numbers function, returns back a result. We'll see if the result's equal to 5 or not, because it should 2 plus 3 should equal 5. And if not, return an error. And we can run our test. We will go to our sample code, add our directory, type go test, and our test fails. Incorrect result, expected 5, got 4. And sure enough, go back to our source code. We can see we got x plus x should be x plus y. And we'll change that, and we'll rerun our test. And now it passes. All right. And so what you see here, let's go back and look at your test function. So if t.error is what reported back the error. And this is a lot like a func.print call. You take the parameters into it, and it just prints them out for you. And we'll see a couple other ways to report your errors in Go functions, in Go test functions in just a little bit. All right, so let's see. So if you wanted to do something with a printf style instead of doing something with just the print style, you can use errorf instead. So here I can copy this out of the book, and we'll run this instead this way. And I'll paste this in, and it looks similar. And I'll put the bug back in again, and I will call go test, and it fails, and the format is there instead with using errorf, and you just like using a func.printf. So besides error and errorf, there's also fatal and fatalf, and the difference between error and fatal is whether or not the current function stops executing. If you use t.error, the rest of the code inside your function will continue to run. If you use fatal, the function stops at that point. This doesn't stop all of your tests. This only stops that current function's test. And so the question becomes, when do I want to use error and when do I want to use fatal? And the answer really is, it depends. That's always the answer in software engineering. It depends. In this case, it depends on the data that you're testing. So if I say I have a function that's, I'm going to call a function to test, and that function returns back a struct and returns back an error. And I expect to get that struct back, and I want to test the fields in the struct have the values I expect. If that function returns back an error, I want to do a t.fatal because I can't go on and do any more testing. I don't have the data to test against. But if I have other tests inside that test function that are testing the values of the individual fields inside of that struct, I would want to use a t.error most likely, because each individual field is independent. I want to gather as many possible errors in one test run as possible. I don't want to just like stop on the first field with a bad value. If I have fields A, B, and C, and A and B both have bad values, but C doesn't, I want to catch both A and B having bad values at the same time. I don't have to wait and run the function a second time and then find the error in B and then find it's all good. So think about how you're testing, how to speed up your testing, and then that's how you decide to know whether you use error or fatal. In addition to setting up your functions, you can create some setup data for it as well. So let me show that as well. Pop over here to our test main example. And so if you have some setup data that you want to use that's going to be used across multiple tests, create a function called test main. You get one of these functions per package. So you have multiple files with different tests in them. You would only get the one test main across all of them. And it's like test takes in a testing.t, test main takes in a pointer to testing.m, and usually you call it m. And what it does is you have a space before, you set up stuff for your tests, you call m.run and get the exit value, you clean up from your tests, and then you call os exit with the exit val that was returned from m.run. So you must follow this basic structure. And when you do that, you're able to set things up like package level variables that can be read by both of your testing functions. And so we have here our test time function, and we're going to read it in both test first and test second. And when I call go test on it, test main, and say go test, you'll see it's the exact same time down to nanoseconds that we got in both functions, because we set it up exactly once. Now, here's the thing about test main. If you are using it, think very carefully about your code. It's useful in basically two situations. If you have like an external repository, like a database or other resource that you need to set up that you're testing across multiple tests, or if you have code that depends on package level variables that have to be initialized. So in general, I mentioned this repeatedly in the book, avoid package level variables if you can, especially if they change value. If it's a constant value set up once, that's fine. But if you have package level state that's mutable, that means that you lose track of how data is flowing through your programs because you don't know exactly what could have possibly changed this global store of value. It makes it a lot harder to understand what your program is doing. It's often a source of bugs. So, and if you are using it because you have these package level variables that change value, look at refactoring your code, look at how you can clean things up to solve that problem. There's also a cleanup method on testing.t that we can use. So if you create things, you can clean them up in your code. So let's say, for example, I have a function called test file processing, and I'm going to create a file, and then I want to have that file cleaned up for me automatically. And so this create file function that I've written here, it takes in testing.t, and it's going to return back the name of the function of the file that we're creating, and we use OS_create to create a temp file, and we're going to join our errors together if we have any errors. And here's our t.cleanup function. So t.cleanup, you pass it a closure that's going to run when the test completes. And so test file processing, when it finishes running, it will call test.cleanup's closure automatically for you. And we can run it, it'll do nothing. So we can go test cd/cleanup, and we'll do a go test -name equals test file processing. And oh, I got the wrong syntax for it. Test that. It's probably doing it live. So yeah, it will clean up automatically, and there won't be a file left behind. I can run it from the IDE directly, and it runs it, passes, no files created that you see. Now, because creating files is such a common pattern, there's actually built-in support in Go to create a tempter. So say t.tempter, it creates a temporary directory that you can then use to put any files into. And anything in that temporary directory that you create with t.tempter will be deleted automatically when this function exits. So we have our function here, create file with create temp. We pass in our temporary directory, and now we can just create the file. And there's no need to do any cleanup code for ourselves by hand. But if in general, you have something you want to clean up that exists just for the space of your test, use those functions so that you're able to clean up nicely, not leave stuff behind. All right, environment variables. So it's a really good practice to use environment variables to configure applications. If you're familiar with the 12-factor application, this was a pattern that was first described in the early 2010s. The idea is that you externally configure your application, and environment variables are a great way to do that. And because you will use environment variables to configure your code, you may have tests that have to test code that depends on environment variables. And again, Go supports in the testing library ways to test it. So I've got a quick function here called process mvars. It looks for one called output format, and then returns back a config, which is a struct that has output format as a field. And I want to test to make sure this function works correctly, but I don't want to mess other things up that may have set that value. So you can use the set env function on the method on T. And you give it the key and the value, and then we call process mvars, and it will work correctly. And the nice thing is this will automatically reset the value of output format when you leave this function. When the test function ends, if output format already existed, it would go back to its old value. If it didn't exist, it would go away. And so this code now works correctly. env, and we can say go test, and it will pass. All right. So in general, again, some advice for writing your programs. Environment variables are great for structuring and formatting for providing functionality for your code, for defining your configuration. But don't read those environment variables like 25 levels deep into your program. Try to isolate the code that reads environment variables, something called very soon after the program launches, and then pass a config through your program instead. The reason why is you might want to test it without having these environment variables being set up. You may want to reuse that code in a place where the environment variable isn't set. So think about how to isolate that environment variable usage to some small part of the code. And there are also third-party libraries like Viper and mconfig and go.env that make it easier to work with environment variables. So look at those and see if those will make it even easier to configure your programs for you. Sample test data. So one of the nice things about Go is that it did think about the fact that you do need some test data for your programs as well. And to do that, there's a magical subdirectory called test data that you're expected to put your tests into. And this is a fun fact that I learned while I was giving other versions of this talk, is that why does Go specify this special directory just called test data where your tests are going to go? And you can see in our text directory here, we have our sample file here. It's Spanish on Italian. I'm sorry, that's what I went with for the book. And the reason why they had this test data directory set aside is the Go team had to write tests that involved Go code. And so they're putting .go files that they wanted to use just for testing. And so they need a way to tell the compiler, don't look in this directory for compiling your code. And that's why test data exists as a convention and is enforced by the compiler. And so if you look at our text program, we're going to count the characters in a file, give it the file name, give back a rune count, very straightforward. And here we're going to look in our test data directory to read from it. One thing to notice is that this path is relative to the directory you're currently in. So if you're running Go test across your whole code tree, you don't need to have the full path to your current directory to use test data. Just the relative path works perfectly fine. And we're going to test sample 1, which you saw exists inside of here. And we're going to also test no file, so the file doesn't exist. And this test will pass. So we can text, and you go test, and our test passes. All right. Let's see, any questions pop up? All right. All right. Caching test results. This is something that is good to know. If I run that test again, say go test dot, and run the test more than once, notice this is cached the second time. And the reason for this is Go is trying to be as fast as possible when you're running your test. If you have a large code base and you change one file in there, you don't want to have to rerun every single test, every single directory. So Go will cache the results. And if you modify any code in that, any source code, or you modify anything in the test data directory, it will invalidate the cache and will rerun the test for you automatically. So if I then, put a space in this program and ran it again, I can move it. I can add a hello and run it again. It'll be uncached, and then it'll cache it again. So one thing to note is that if you just say go test by itself and don't give it a path, it will always rerun the test from scratch. Normally, if you're testing a whole source tree, you'll say go test ./3 dots, and that'll walk a whole source tree directory to test it. In that case, it will be cached. Other times, if you want to say go test -count equals 1, and you say ./.. it will also not cache it. So if you ever have to not cache for some reason, you're testing the whole source tree, use -count equals 1. All right. So testing your public API. We have our pub adder function here we're going to look at. So let's say we want to test a public function. We want to make sure we're only testing things that other people can access that have been exported from your package. And so with this package pub adder, it has add numbers again, X and Y. This time there's no bug because we saw how that works. So we write our test for that. It's still in the same directory as our adder public, but now we say the package name is package_test. And this is the only time in Go that it's legal to have a different package name for a file in the same directory as the rest of your package. This _test is a special case. Notice, I will show you, you have to import the package, just like it was external code living in a different package entirely. And when we use it, we say pub adder dot to access add numbers. Remember back when we tested adder before, we were in the same package, so we don't have to put adder dot here. But when we're testing it publicly, when we use _test, we have to import, and we then have to use the import as well. And if you run this, it will, of course, work. There we go. So this is very handy to make sure you're not accidentally trying something that's internal, that's not unexported. Mostly it's just there to keep you honest on your testing. All right. All right, go-cmp. This is my favorite third-party library for doing testing. There's reflect.deep_equal that exists in the standard library. I talk about it a little bit in the first edition. In the second edition, I mostly tell you to avoid it because there's much better tools that are around. And one of the better tools that's around is a third-party module. It's actually released by Google, but is not part of the standard library, called go-cmp. And what this will do is it will compare your code for you for your complicated comparisons and returns back a detailed description of what doesn't match. So let's take a look at how to use go-cmp. I've got this type. It's a person struct, and it's got 3 fields, name, age, and date added. And we have a function called createPerson that takes in a name and an age, returns back a person. And we set the name and the age, and the date added is the current time. So I want to run a test to make sure that my createPerson function actually works, as simple as it is. And so, oh, there we go. Here's my test. And I'm going to be using cmp_diff. You import it with github.com, Google, go-cmp. And we write some expected value. And we're going to call createPerson. And then you use this pattern to call it. Say diff : equals cmp.diff. You pass in the expected value and the result you actually got. And then you say if the diff is not equal to empty string. So diff is a string. And if it's an empty string, the test passed. It was matched perfectly. If it doesn't match, you get back an error. And you then use that string to print out an error. And let's see what happens here. We run this. You're actually going to get back an error because the date added, right? We didn't put a date added in here, But create person, it always puts in a date. So the nice thing is, CMP showed us exactly what lines were not matching. We have the date added, and we have it marked off here. So how do we fix this? So one of the nice things that this package gives you is you can write your own comparator function to define things. So I can write a comparator function, cmp.compare, you pass it a closure again, takes in x and y of type person, returns back a bool. If I was comparing a struct of type foo, this would be a foo here instead. And then you say in your compare that you write yourself exactly what field you want to compare. And then when you call cmp diff, you pass in that compare as a third parameter. And we're going to add another test to make sure the date is not, if the result of the date is 0, then date added wasn't assigned. That's all we can really tell, is that the date added should have been set to something besides the 0 value. And if we run the test now, it passes. There's a ton more things this package can do, but it's a very nice way to write your comparisons for comparing structs, comparing maps, comparing slices. Anytime it's more difficult than just like a single primitive type you want to compare with something else. All right, let's see. Next topic, making pretty good time. Table tests. I love table tests because oftentimes when I've got a function, and we'll take a look at our function we're going to write, it's in the table package. This function has a bunch of things going on in it. And I'm just going to do some math. You're going to pass it 2 integers and an operator, which is a string, and we'll pass back the result of running that operator on our 2 integers that were passed in. And I want to test this program to make sure that it works correctly. So I'm going to write a table test. And with a table test, I'll show you what it looks like without a table test first. Then we'll division for unknown operators here, division divided by 0, we'll cover that case. If you don't have a table test, you'll have code like this. All right, result equals do math plus 4. Error not equal to nil, great. Result error 2. 2 minus 2 is 0, right? Over and over again. This is really hard to see. Where is the actual testing going on? You get kind of blinded by all those if statements, and you're very repetitive, right? I mean, I'm doing the same operation over and over again, and I shouldn't really have to repeat myself on this. And to avoid that, there's a convention in Go called a table test. And what you do is you declare a slice of an anonymous struct, and we have a name field. Talk about that in a second. And we have our inputs, num1 and num2 in the operator. We have our expected output, and this error message string to see if an error came back. And I'll talk about that in just a little bit, some ways to make this even better. And once we define this struct, we define a slice of values that go inside that struct. And so we have addition, 2, 2, add, should be 4, no error. Subtraction, 2 minus 2, get back 0, no error. Multiplication, 2 times 2 is 4, no error. Division, 2 divided by 2 is 1, no error. And 2 divided by 0, bad division. Right? And now we have our data source. We can loop over it, use a for range loop. And we use another method on T called run. And you pass in a name, and then you pass in a testing function as a closure. So you have function T, it's pointer to testing T, and then I run the test. And it's just like any other test. Instead, I'm just going to pull the values out of D. So we use the num1, num2, and op that we defined here, get back our result, and see if it matches what we expected. And if it didn't match what we expected, return back an error. And then we'll compare the error strings. If the error strings didn't match, we'll report back the error didn't match as well. And we can run this. And the nice thing about a table test is we get this nice information of exactly what possibly could have failed. So it's broken up into different parts. If we look at running the do math test, it's just one function, right? So if like something broke halfway through here, if I had, I said that 2 minus 2 is supposed to be 1, and this function fails, I just know that it failed, right? I don't know exactly which operation failed. It's not labeled well. I have to jump into the code and say, oh yeah, this is 0. And we can run this again, and it will pass. So one thing I want to point out with my testing here is that I tested the strings that came out of it, right? I get returning back an error, but I'm testing just against the error string. And that's not great. There's better functions now in Go with errors is and errors as. So let's see what it looks like. This is some live coding. Hopefully nothing breaks. Let's change this a little bit. So we're going to go to our table function. And instead of saying errors new division by 0, we're going to define a sentinel error. And it's going to be error div 0. Look at that. Gotta love GPTs. And instead of saying errors new here, we can just reuse error div 0. And we'll talk about that later. No, I'm talking about this. Yeah, we'll cover that in a little bit. So let's look at our table test. Instead of saying error message here, let's just say error. Type error. And now we're going to fix our code to change this to be a nil, and a nil, and a nil, and a nil. Instead of the name, we can actually use our sentinel here. We can say error div 0 we expect to get here. And this whole code here now gets a lot simpler. We're going to say if not errors.is, then we can say, take our, t.error. And this should actually be, yeah, there we go. And we can delete all this code here. And it works. So this is actually safer and actually shorter and easier to understand. If it's not the same error, then it fails. Then we can run this. Oh, error call has, oh, they wanted error F. There we go. Good job. And run it again. Oh, got %v. Sometimes you can't trust your GPT to do the right thing. All right, there we go. And it works just fine. We now have a type safe error we can check against. And actually, this is a little bit better because this is more declarative. And we'll come back to this example later on. All right. So running tests concurrently. When you use the test library by default, it's running your tests in series, like one test after another, one after another. All of our computers have lots of CPU cores. What I'm on is 16 cores right now. So you maybe want to run some of your tests in parallel. And you do that declaratively. You just add this line t.parallel into your tests. And that makes your test get scheduled in parallel, independent from your other tests, which is nice because your tests should all be independent anyway. They shouldn't depend on each other's data. And that can make your long-running test suites run a lot faster. So if you have shared mutable state, this is going to be a problem because you'll get inconsistent results. Like I said, shared mutable state is a really bad idea. If you set env and your test is parallel, that will panic your code because it doesn't know what to do. But table tests in parallel get interesting, especially with older versions of Go. So let's look at our testing of a parallel table. I have this in the parallel directory. Bring this up. So I've got some code. It's a function called toTest, just adds 10 to the number, right? Pretty straightforward. And I have a data structure. A, B, and C are my 3 tests. And I'm going to take that out. A takes in 10, returns 20. B takes in 30, returns 40. C takes in 50, returns 60, right? I declared to run in parallel. Because these are all pretty independent things, that's a really simple function. But let's see what happens when I run this test. Let's look at the output of it. So it tested 50, 60, 50, 60, and 50, 60. Never tested 10 and 20. What happens with 10, what happens with 30. And the reason for this is because of how loops work in Go. So when this variable D is being shared across every single time this closure is being called, and because we're running in parallel, they all get scheduled to run after this loop completes. And they all see the exact same D with the exact same value assigned to it, which is the last value assigned. And this is a tremendous problem. This doesn't just happen in testing. It happens all over the place. If you have a for loop and you have a go func in there and you're looping over that value that was in that for loop, the key or the value, you probably hit this bug. And it's such a big problem. The Go team actually decided to make a backwards breaking change in Go to fix this problem. So if you'll see here, we're using Go 119. If I change this declaration to say Go 122 instead, and I rerun this code, and now it says 10, 20, 50, 60, 30, 40. Because there's a fix in Go 122 for this. They made sure you have to opt into it by changing the value for Go in the Go mod file to Go 122. Yes, correct. It has been fixed, and that's exactly right. It's opt-in. They want to make sure it doesn't break any of your existing code. And this was really pernicious. Like if this happened in your production code, it was probably fine. But mostly test cases were failing because you weren't actually testing what you thought you were testing. So it's really nice to have this ability in here. What happens is if the Go compiler detects in Go 122 that this variable is being captured, it will create a new copy of that variable every single time the loop happens, so that you have independent Ds and not sharing a D. and that way they can each get their own value instead. So remember that in general for your loops in Go. It's important. It's nice for testing in parallel. All right, code coverage. Code coverage is one of the more important things. Code coverage is necessary but not essential, right? Just because you hit 100% code coverage does not mean that you have no bugs in your code. And we're going to see an example of that in just a little bit using our table package again. So again, Go includes code coverage as part of what's built into its testing package. You say go test -v -cover changed packages, so I'm testing the right package. Table. All right. And you say go test -v -cover cover profile equals c.out. And we run this. It passes 87%. And we'll see you create this file called c.out. That's got some information in it. And now let's see what's going to pop up. We say go tool cover -html equals c.out. And this works correctly, hopefully. I will pop this onto the main screen. Code coverage information. If you are colorblind, red-green colorblind, I'm sorry, this is the colors they chose. It was a surprising choice because Rob Pike is in fact colorblind. And so he can't see this terribly well, but things that are grayed out are things you don't test. Things in light green are things that have been tested, and things in red are things that are not tested. So we can see we never wrote a test to cover this one line. So let's go back and write a test to cover that line. And we'll go to our tests. And I'll have this already in the book, so I'm just going to copy it out. I want to test having a bad operator. So let's add a bad operator line to our test cases. And what we're going to do is paste this in here. And this is going to be, and we're going to switch this over to error. So we're going to go back to fix this up. And we're going to have a new type called unbad op error. It is a struct that has a field called op. And instead of doing fump, and we're going to make this into an error. Look at that. All right. That's good. We don't have to make that a pointer, so that's good. And we're going to change this from being fumped error f unknown operator. The text should be unknown operator. Make sure it matches. Want to keep things consistent. And instead of saying fumped error f here, we're going to say bad op error and pass it the op. And in our table test, for our error, we're going to instantiate a bad op error with a question mark. And we can rerun our test. All right. And we can do our code coverage again. And we will see that, in fact, we now are covering that case as well. If someone passes in a question mark, not a known operator, we cover that. We're not testing our error function here. Not that important, I think, to test it, but you can write a test to make sure that it matched the output correctly. But the thing is, there's still a bug in this code. We have pretty good code coverage, 100% in this function for do math, but there's still a bug. And let's add another test case so we can sit there and see what that bug actually is, if you didn't see it yourself already. So we're going to add another multiplication case. Oops. Here we go. And we'll make this error nil because we expect that 2 times 3 is in fact 6. And if we run this, I'll run it from here, got an error message. Expected 6, got 5. That's not great. In our code, instead of times here, we need a plus. So that wasn't great. And now we can rerun our test again, and the test passes. And you can see another mult is covered as well. So again, just because you have full code coverage, be careful. It's a good thing to get there, but you may still miss bugs in your code. It's not a 100% guarantee of anything, but it's nice that the functionality is present. All right. So fuzzing. I don't know if anyone here has heard of fuzzing before, but this is one of the relatively newly added to Go. It's about a year ago, was added into the standard library. It's really neat. The basic idea is that all data is suspect. So what programs really do is they take data in, they convert it, they spit some data out somewhere else. That's the job of programs. And the thing is, the data that comes in, you can't really trust it. No matter how well specified a format is, eventually something's not going to match. It doesn't have to be malicious. It could be someone trying to hack you. It could be the data is corrupted in transit or in storage or in memory. The program could have a bug that generated the data. Your program might have a bug. Data format specifications aren't always crystal clear. There's always some kind of corner case. So it's impossible to think of everything when it comes to testing code, right? We saw that with the previous example where we missed something with our code coverage. And so what fuzzing is a way to write better unit tests that will automatically generate some tests for you that will cover cases that you missed. So fuzzing is a technique for generating some random data and submitting it to the code to see whether your code can properly handle that unexpected input. You provide what's called a seed corpus, a set of known good data. And excuse me, the fuzzer uses that as the basis for generating random data. So let's say we've got a program that processes files. Parse data is a very simple function. It's going to takes in a reader. It'll scan it. The first line that comes in should be the number of subsequent lines that are going to come in. And then every line that comes in, just a string we're going to capture. And then we return back the slice of strings that we got in. And our code looks pretty good, right? We see if it's empty, we return back an error message saying it's empty. They're looking to scan. Look at the first line, look for the number. If it's not a number, we return back an error. We then pre-make our slice to the right side with the right capacity for it. We then loop over that count we got. If there's no line available, if they said there were 100 lines, we've only gotten 3, that's an error. Too few lines. Otherwise, we take the line, append it to our output, and then when we're done, we return our output. Pretty simple function. Looks pretty good. And we got a test for it already. And this test, simple, give it 3, say hello, goodbye, and greetings, get the output. If it's empty, get back an error message. If it's length 0, it's 0. If someone doesn't give it a number, they just say ASDF, we give an error message back saying that it was on a number. And then if they gave an incorrect line count, we have an error to check for it. And this test works. I'm going to rely on the built-in code coverage in IntelliJ. It runs it. Our tests all pass. We look at our function. 100% coverage there, right? It's all green. So looks like we thought of everything, but there's probably some things that we missed. And this is where fuzzing comes in. And so what you do, let's look at the fuzzing code. No, that's the, let's go through that. Let's fix code. All right, here we go. So when you're writing a fuzzer, just like a test function starts with the word test, a fuzz function starts with the word fuzz. And it takes in a testing.f, we usually call f. And what you do is you give it, like I said, that seed corpus, some initial data. And our initial data is going to be a slice of bytes saying hello, goodbye, and greetings, and 0 is empty. And those are good data for it. And so we declare some test cases. And then we're going to loop over our test cases, and we're going to add them. We call the add method to add to the seed corpus. And then we call f.fuzz, like we called t.run to run tests before from the table test, use f.fuzz instead. And what f.fuzz takes in is a function which has a testing t, and then it has one or more parameters after it. And these parameters match what was passed into add. So if our function needed more parameters, we can actually pass multiple parameters in for the test data that we need to test our code. And none of the stuff can be validated at runtime. Your code will, if you do this wrong, it will panic. Just have to get used to doing it correctly. And when it's only one, it's pretty simple. Just one slice of byte for everything. And you can't use any data type. It's primitive types, basically strings, numbers, Booleans, and slices of bytes, I think, are the only thing you can do it with. So in our testing function, remember, we can't, because the fuzzers can generate random data. We can't test for what we expect to come in. We can only see if we fail to handle some random data correctly, if we fail to do it. So we have to think kind of backwards for usual testing. And what we're going to do is we'll create a bytes new reader off that slice of bytes, and we'll call our parse data function. If it errored out, that was good. If it got bad data and errored out, that's fine. I have this toData helper function that will take the data from a slice of strings, turn it back into that slice of bytes we got initially. And then we'll round trip it. We'll call it again, try to parse it again. use our CMP diff function to see if the exact same things happen twice. So if we round trip well, that looks pretty good. Like that looks like the function worked correctly. If it errors out, that's not so good. So now that we've written a fuzzing function, again, we're not testing for positive results. We're only testing for negative things to happen because you can't test for positive things to happen with a fuzzer. And so make sure I get the syntax right for this. I'm going to scroll down a bit. All right. You say go test dash fuzz equals fuzz parse data. And you can only fuzz one function at a time. So you give you the name of the exact function you're going to fuzz. And we run it. And run for a bit. It crashed. All right. Let's see what happened here. Make slice cap out of range. And it created a file named fuzz parse data. You look in our test data directory. We see fuzz parse data, 03, F8, 1B. Here it is. And this is creating test cases for us. And we can see what I tried passing in was -1 for the length of our data coming in. So that's not great. If you try to create, if you go to our file parser and you try to do a make and you use -1 for the count, that's not good. So we've tested for this before. If count is less than 0, let's error out, right? So this is good. I found an error we had before. So we'll add this error case here. Looks good. Let's go back and fuzz it again. Oh, all right, failed again. And we can look at the input. We got this time, it's B605C. And you can see it took in 1, and then it has a bunch of empty stuff. Then just a bunch of empty lines. All right, we don't expect empty lines to come in. That's not a great experience. So let's make sure if we have any empty lines that are passed in, we just error out in that case. And so we'll scroll down to our fixed code that I already wrote. And we'll see. When we have a line, we'll trim space and see if the line length is 0. And if it is, it's an error. It's a blank line. Now I'll pop this into the right place up here. All right, second problem we found. And let's run our fuzzer again. And let's run for a bit. And we should eventually get to another error. There we go. All right, fuzzing process hung. That's interesting. And here's the file it created, 124. All right, it's trying to create a file with this long, right? Yeah, so that's a lot. 30 million, that's a really big string. That's not gonna work. So let's change that. Let's go back and fix our file parser. And we are now going to make sure that we don't have too many things being passed. Let's say 1,000 as long as we want to go, because we want to have fun passing gigantic numbers and have it work. And so our count's greater than 1,000. It'll stop. All right, let's run it again. Let's see. All right. All right, we can let this run for a while, but this is random data is being thrown at it. What I've seen in the past, it's not going to find anything else. If I let it run long enough, maybe it will, but usually I cut it off after a bit. You can specify with parameters how to specify how long the fuzzer runs for. Yeah, that's about enough time. All right, so I didn't find anything else wrong with our code, but now I found some 3 really good errors that we had in here that weren't obviously errors before. And again, just like with code coverage, there's no guarantee the code is now bug-free, but we're able to find some stuff that wasn't found before. And that's really the value of fuzzing. And you get these nice test cases created for you automatically, which you can actually run yourself. Like actually, if you see a test case, you can say go test and run it, and it'll tell you if it passes or not. So you can do that, and it will. Oh, all right. So last thing I want to talk about today is benchmarking. Let's go back to here. So running your own benchmark to figure out how fast or slow your code is, it's actually kind of difficult. And rather than doing it by hand, what you should do is rely on Go's built-in benchmarking support. And so we have some sample functions here. Very simple function. File length returns back the length of a file. You pass it in a file name and a buffer size. Talk about that in a bit. Open the file, defer file close, and then we're going to read from the file, count the number of bytes, and then return the count of it. Simple, straightforward. So let's write a test to see how this works. Something I want to talk about actually here first is I needed some data for this test, and I didn't want to check in a really big file. So what I did is use test main to make data for me. And so make data is going to create a file in test data.txt, random seed. I know from this random seed of 1 exactly how big of a file it's going to create. So that little make word function will create exactly what I expect. So since I know by hard coding the seed exactly how big of a file I can get, I can pre-create random data and not have to check it into source control. It's a little trick. And so we have test file len. We write a regular test function to make sure the code actually works, and we can run it, and the code works. But how fast is it? Like, what are the optimal values? Going back to here, this buff size, is there a way to optimize this buff size to make this program as fast as we need it to be? And so that's where benchmarking comes in. Now, the thing with optimization is only do it if you have to, right? Optimization is not a thing. The goal is not to make your program as fast as humanly possible. The goal is to make your program as fast as you need it to be. And need depends on your business needs. It depends on if your customers are happy or unhappy with the experience. Depends on other things you have to do as well. If you want to like make your program a little bit faster because you're adding new functionality in, and you want the total experience to stay about the same in length, that's where benchmarking and trying to make things faster is important. But just making your code faster for faster's sake is often not the point. So let's see how to write a benchmark. We saw with test and fuzz how you prefix with a word. So here we're going to prefix the word benchmark. And with file length 1, now it's testing.b instead of testing.t or f. And you loop like this. And so this is something that is, so you say for I equals 0, I is less than b.n. Because what the Go benchmarking does is runs the test enough times to make sure that the results are stable. And so it has to loop repeatedly over your function and increases that number until it's stable. And so we're going to call our test data.txt with a buff size of 1. If it errors, it's fatal. Otherwise, we're going to write the results to what I call the black hole. And this is me taking advantage of the fact that package level data is hard to track. I know the Go compiler can never optimize away anything to write to a package level variable because it doesn't know if something else is going to use that value somewhere else in your program. And so just in case the Go compiler gets smart enough to say, hey, you return back result, but you never used it, I think I can throw away this function. If you get to that, so if Go compiler ever gets that smart, this would get very, very fast in our test, but it wouldn't actually be very fast. It wouldn't actually be testing anything and getting any benchmark information. So when I'm running a benchmark, I always use a black hole to store the result. Go compiler is not going to get rid of this one, but just as a general practice, I tend to follow this. And we can run this benchmark. And we can see the output. I also have a table test as well, so we can test the same benchmarking. It's a very simple kind of table test. 1, 10, 100,000, 10,000, 100,000 for the size of the slice I'm using. And use b.run instead of using t.run to run benchmarks as a table test, and use testing.b instead. And so you say, we're in the bench directory, go test dash bench equals dot. And, oh, I actually want to do something else on this. So we get back our numbers for how long it takes for things to run. In fact, I forgot a parameter, benchmem. That will tell us how much memory we're using as well, and how many allocations we are doing. And again, we have nice names for things with the table test version of this. So that's really good. So the first column is the name. Second, and at the end here is the number of cores in your computer, by the way. This is the number of iterations it took to get to a stable result. This is the number of nanoseconds for each of those stable results to take. This is how many bytes were allocated. And this is how many times allocation had to happen. And so you can see this is long. Around 10,000 seems to be at the optimal one. This is the fastest one. Uses a bit more memory than these other cases, but it uses fewer allocations. It's pretty fast. This one is a little bit slower, uses more memory, but fewer allocations. So this feels like this is probably a pretty good solution for the cases we actually have. And it's nice we get this data out automatically, so you kind of know what value to pick. There's actually, I'm not going to talk about profiling today. One of the things you can also do if you have profilers in Go is you can look at this and say, huh, that's a lot of allocations. What you might discover is this line doesn't belong here. This line really should be outside the for loop because we can reuse that buffer over and over again. And if we make that change to our code, we can do benchmarking again. And now we're going to see a couple of things. First of all, it uses a lot less memory. And constant number of allocations every time, which is fantastic. Uses a lot less memory to do things. It's a lot faster than before. It's about 30-40% faster. This was 14,000 nanoseconds. Now it's 10,000 nanoseconds. And it's still the fastest case. So if you're reading a file of around 60,000 bytes, 10,000 byte buffer is about the right size. So if this works for you, then those are the right answers. And this is why these tools are so useful, to help you focus on what the problem is you actually have to solve, not just make guesses about what you think are the actual problems that you have in your code. So that's all I'm going to talk about for today. But if you're in the book, in the testing chapter, I'll show you the table of contents for it. There's many more topics. We also cover using stubbings, so how to stub things out in Go, HTTP test, which is a fantastic way to test your HTTP client and servers, how to group your tests, create integration tests, and use build tags, and also using the data race detector to find concurrency problems in your code. So yeah, that's thanks for your time. That's what I had for you today.
Hey, we are again. Thank you, John. Thanks a lot. It was very enlightening, actually. So we have some questions in the chat, and I don't know if you want to keep sharing. Maybe it helps to give some context. I'm not sure. So I'm going with the first one, and
okay.
I don't know if you can see it.
This was back at the error is, so more or less halfway of the presentation.
Yeah, let me turn screen sharing back on so I can show this. This works correctly. All right, can you see my screen again? All right, okay. Fantastic. All right, so we'll go back to our table example, which had this in it. So you asked, why did I use the bad op error as a struct? And that's exactly right. I could have, I wanted to be able to capture the operator that actually happened, and that's the difference between using is and as. So this is, in the errors chapter, I talk in more detail about sentinel errors. So error div 0 is a constant thing. There's no need to redeclare it over and over again. So making it a package level variable that is effectively immutable. In theory, someone could do something bad and like reassign the value to this. If they do, they're a jerk. You'll catch them during code reviews, I hope. But let's just now test things exactly against the error itself using errors is. And because the bad op error could be a different op anytime, I did a question mark in my test, but it could be anything. You want to capture exactly what went wrong. And so I can print it out and give more contextual information to the user.
Super. So one more question was about some frameworks and libraries, for example, Ginkgo and Omega.
For writing tests against the REST APIs, the HTTP test package is what I use an awful lot. I tend to use Chi as my package for writing HTTP test for writing REST endpoints. Chi is nice and lightweight. And now there's actually one of the things that was added to Go recently. I think it was 121. Maybe it was 122. They added in better router support, so you can actually have variables in your router paths. So even using things like Chi, is it 2? Yeah. That added it in. So sometimes you may not even need some of the other packages. I would try as much as you can with HTTP tests in the standard library. And if you don't have something that works for you, then try something else. I don't actually know all the libraries off the top of my head.
Let's see. We have one more question. Interesting. So fast testing in CI.
It's a good question. You can cap how long fuzz testing takes. So I would do it periodically. I wouldn't do it always. Like when you're first writing the code, maybe a good time to do fuzzing, maybe towards the end to make sure, but in the middle, you probably don't need to do it. It really depends on your company's practice. It depends, like everything else in software engineering. And you can cap how long it takes to control C out of it.
Super. Do we have one more question? I don't know if Claudio, do you want to ask something or?
There's Thor. There's a Thor. Maybe not the Thor. That's Just one. This asking, this might be a silly question, but do you commit benchmark tests or you just use them as a local tool? Am I guessing the latter?
Yes,
Yeah.
that we should.
I would commit the benchmark test, even if you don't run them. Even if your CI test is not running your benchmarks, other developers you're working with will probably want to run the same benchmarks as well, see if they've made a change that is affecting the code that you've already benchmarked before. One thing I didn't show, I kind of wish I wish I had infinite pages in my book. There's a great tool to compare benchmark runs between multiple runs. I forget the name of it off the top of my head. So you can run benchmarks, capture the output, run them a second time, and get the differences over time. So that can be very helpful to have benchmarks checked in so you can run those tests and see, are you getting better or worse? And anyone can do it. In general, Go is very focused on GitHub being like, or Git, but really it's all GitHub for us now, as a place like manage your code from. Anything local means if you leave the company for whatever reason, it's gone. So get things checked in. That's why like even modules you depend on, packages you depend on are always checked in to source control, because it gives a way to make sure they're doing good software engineering practices and your code's being tracked.
As well. Yeah, I think that's the wise choice. All right, I think we're kind of closing up. Yes.
Yeah, it was just the last question that came up. I don't know if we have time. Maybe.
Sorry, Kishore. Regarding the benchmark, why should it be committed? They can differ based on the hardware, right?
They could, but it should be relative. This is a yes and no question. Yes, some things in the benchmarks are going to vary based on hardware, but you should benchmark on something resembling where you're going to run in production. And again, it can't be kept locally if it's on your developer machine only. Hopefully your developer machine doesn't look like production. Datadog does not run on MacBook Pros in production. So you want to have your test checked in for that reason alone. They want to benchmark exactly how it's going to perform in the close to real world as possible, some staging environment, or some server that looks like staging. And it should be relative. Like, yes, there are better memory subsystems or something that may make the test be different in some cases, but I think relative numbers are probably going to be about the same.
Makes sense. Yeah.
Thank you. Thanks, John. And yeah, I just want to say that I'm pretty amazed by every time by the test package. The Go team really put a lot of effort on it compared to other languages maybe, and I sometimes often discover something new. I don't know actually about the CMP comp package, and also I just discovered maybe a couple of years ago about the thelper function. I mean, sometimes you just discover something. It's pretty helpful and useful.
Yeah, we definitely never write enough benchmarks and fuzz tests. Exactly. That's something I promise myself every time I touch the subject. And then, however, time is limited. Well, that was amazing. Before we close, I want to steal a couple of questions from my favorite podcasts, like Cup of Go and Go Time, that have this nice thing to me. At least it fosters discussion. So if you had the chance to, like, if you had a magic wand and you could add or remove a couple of functionalities from Go, what would they be?
The one thing, number one, is more immutability. So in Go, there's no great way to declare things are immutable. You kind of cheat by not using pointers in some cases, but you can't avoid that with slices and with maps and explaining slice behavior to people. And this value can change when you pass it to a function. So the value can't change. It's kind of maddening to explain why these things are true. This is why I have a chapter on pointers in my book. It's like there's like 4 chapters in the book. Testing was one of them. Pointers was another. Where like the book is written around those chapters. That was why I wrote the book, was to cover these concepts that weren't covered well other places. Yeah, having a better immutability story, having the compiler enforce immutability, having when you declare things that are constant Go, they're things the compiler can determine at compile time as being constant. It's not things at runtime where I say this. I put 3 values in the slice. The slice will never grow, and none of the values inside the slice will ever change. I can now pass through the code and be sure nothing's going to mess with it. You can't do that in Go. You have to just basically hope that no one messes with your stuff. It would be good if that was there. That's number one to add. My language geek wish list has some types on it. The current Go enums are terrible. And other languages like Swift and Rust use some types as a way to do enums that are type safe. And the introduction of generics opened the door to the possibility of adding some types, but it's not happening anytime soon.
I think I lost count of the amount of proposals of enums that were rejected. So probably no luck there.
Yeah.
Yeah, I wish for union types as well, but
Mm-hmm.
some people would kill me for saying that. And also, I would like a try keyword as they have in Zig.
Oh, that was a contentious summer in 2019, I think. People proposed try, and then it got booted.
Bummer. All right. Very last thing, Enrico, would you like to go on for the raffle? And
yeah, let's see.
We close up.
So let me share. So we are going to do this live, and obviously I'm very sorry, John. I don't have tests for this. I'm very sorry. I should have written some tests for that. I will do it. I swear. So I just have the emails that the user submitted, and so if you want to check the code, I'm not trust me, I will push it as well. And let's see who are the 5 lucky winners of the
drum rolls.
second batch.
All right.
Yeah, obviously the emails are obfuscated, but we got the clear text on us. But maybe you can just see if you are one of the winners that just came out. So thank you, everyone. Thanks a lot, John, for your presentation and for and with us. It was very, very, very.
The God of Thunder wins. Awesome. Thank you very much, John. It's been a real pleasure to have you. And read more books, everyone. It's good for you.
Yes. Thanks so much for having me.
Thank you.
Cheers.
Thank you. Bye.
Bye.
Thank you.
Cheers.